You want to make the summary again, as usual. Okay, let's remember, right, what we did on Tuesday. We said we are going to need a couple concepts to be defined, right, for the surface integrals. The first one was the parametrization of the surfaces. So we gave the parameterization of the surfaces by a vector function, which it is this way, right? So basically, like you parameterize the lines, the curves in space using one parameter, but this time, since it's a surface, you need to use, right, the two parameters to give the parameterization like this one. U and V are the two parameters we are using. Of course, you might need to have, right, a boundary for these parameters. They are not gonna be infinite. In some cases, of course, it might be infinite domain. So whatever you do with the surface integral, with the surfaces, the main idea here, okay, is to find the parameterization for the given surfaces, guys. There is other way actually to find the surface area or some other concepts, but the parameterization is the best way to go. I didn't want to get into other type of derivations, the formula given for the surface area, but this is the best way actually to learn the surface integrals. Later, we learned the surface area, right? Surface area. Excuse me. Surface area can be calculated, right? Can be calculated using this formula, if you remember, Tu plus Tv, the length of Tu plus Tv, and ds. So of course, basically, this double integral should be taken over the surface as, but we can just use, right, the mapping idea over du and then dv, and then that turn out u1 and then u2, v1 and then v2, tu, tv, length of, right, this cross product, du and dv. What are they doing outside? So we need these two concepts, guys. Today we are going to talk about surface integrals. And then that's why, okay, we defined these two concepts, parameterization and plus the surface area. We need these two concepts, okay, to define what the surface integrals is. As you remember, right, in line integrals, we did the similar type of things. We learned how to use the parameterization for any given curve. And then we also, right, to find out the length of, right, the lines, curves, using different formula, and then we combine them to get this line integrals. We are following the same path. We are doing, we are using the parameterization, we are finding the surface area, but the problem will turn into, right, something like this. Let me explain, okay, what I will do. And then we discussed a little bit actually when we compare the line integrals and the surface integrals on Tuesday. Basically, when you are given, right, UV plane, right? UV plane, the parametrization will map this UV plane to this surface, right? Let's say this is one of the surfaces I have, and then R will map, right, this rectangular D to this surface, guys. But if I like to talk about the surface integral, I'm basically asking such a question. There is a function here, okay, over the surface. This function could be scalar or the vector field function. And then it represents physically like the heat flow. It represents the electricity flow. It represents any fluid flow, all right, through the surface. Look at that, right? That might be any vector field which it can given. And then this surface can be, right, can be exposed to, right, this vector field. Like I said, this vector field could be electricity, this could be heat, this could be any type of fluid. And then I'm wondering, okay, basically I'm wondering this question. How much fluid flows through, okay, across the surface? Right? If I ask this question, how much fluid flows through across the surface? This is basically, right, a question which I need to, right, to take into consideration the F and then as well as the surface. The part of the surface, right, which is exposed to, right, this function, I can multiply, right, these functions to get the effect of, right, the vector field on, right, this surface. But if I wanna calculate, right, everything around the surface, that is where, right, I need to use the surface integrals, guys. I need to use the surface integrals. That's the only way to go, since you are, right, exposing, right, any point on the surface you have, and then infinitely many points I have. That's why point by point, if you wanna add the effects, integral is actually the main way to go to calculate all of the sum, right? About this question. Like I said, F could be density function. We are going to see today actually to calculate what the mass is if the density is given, right, over the surface, right? The density might change, right, based on the function, and then the density could be different. But if you want to calculate the mass, of course, you need to use, right, the density function over the surface. So the surface integral is the main way to go actually to find out some sort of, right, the fluid effect on the surface. All right, that is why we need to understand how I can use the parameterization in the surface area to define the surface integral. My main job is going to be, okay, defining the surface integrals for any given type of function. Either it could be the scalar function, or it could be the vector field, guys. Since this surface can be exposed to a vector field, or it could be just any scalar function like the density function. Okay. Okay. So let me go ahead and then give you the surface integral definition for scalar function. Surface integral for scalar function definition. The surface integral of a scalar valued function of f over a piece wise smooth surface S is given by this integral S fxyz ds. All right. normally, right, without f, without f, we learn what it means. It means actually that's the surface area formula, right? But now when the f is given, like the density over a surface, right, it might be given as any physical quantity you might want to calculate over that surface, since the rest actually is just the surface area. So this is just a conceptual notation on the left-hand side. Look at how am I going to calculate. I need the parametrization of the surface. I'm going to combine with my function. Look at it. I'm going to use the parametrization in my function. And then also the S part is the area, basically area. And then I know how I can calculate, right, the area of the surface. We discussed this right on Tuesday. This is the part you can calculate the area. Did you see that? That is how I'm going to give the surface integral, right, using the area as well as the parametrization. I need both concepts to calculate the surface integrals, guys. That's it. I hope it makes sense. Do you have any questions so far, guys? If you have any questions before the examples, please let me know. Thank you, Q. All right, let's go ahead and then let me show you first, right, the computational example. Then I'm going to show you, okay, a nice real world examples. We are going to calculate the mass problem actually when you are given the density. Why do you need to use the surface integrals? So first, calculate the surface integral, and then let me show you, okay, how you can use the formula. So please calculate this integral 5 ds over the surface where the surface is given, where the surface is the surface given by this parametrization. U squared and V. And they are in this interval 0, U is between 0 and 2, and then V is between 0 and U. Okay, guys, 0 and U. This example actually made the parametrization easy for us, but always your first step is to find a parametrization for your surface, guys. If you want to use this formula, you see, if you want to use this formula for the surface integral, as you see, right, you need a parametrization for your surface. In this example, the parametrization is given right readily. But on Tuesday, we saw right how to parameterize the functions if you are not given any parameterization. We saw for the cone, for the sphere, for the paraboloid and the cylinder. There was some other examples we found, right, the parameterization for all of those surfaces. But fortunately, we have the parameterization in this example. What I'm gonna do, I'm just gonna go ahead and then look at that, the boundaries. Those boundaries are gonna be for, right, the first U and then V. As you see, since this is the variable, that's why I kept right inside in the double integral. All right. What is my f here? F is basically, right, f function is equal a constant. Normally, I should go ahead and then use the parametrization in my function, but doesn't matter actually for this example, since the function is itself constant, right? That's why the parametrization basically doesn't make any difference since the function is constant. So the rest is, look at that, the TU times TV, length of, right, this cross product, and it is gonna be dV du. What I need here, TU and then TV vectors, guys. What is TU and then what is TV? You need to go ahead and then take the derivative of, right, the given R of T. R of T was, sorry, R function, the parameterization was equal UV, U square V. Let me go ahead and then take the derivative of, right, first component with respect to U, which is going to be 1, TU, and then the third component derivative with respect to U is going to be 0. And also, the vector v derivative is going to be 0, 0, 1, right? Derivative of u with respect to a is 0. Derivative of u with respect to u is 0. And then derivative of v with respect to v is just 1. We should go ahead and then find the cross product right after having these two vectors, I, j, k, and then 1, 2, u, 0, 0, 0, 1. And then we know now, right, how to take the cross product. You need to cross out the first row and then first column. So it is going to be 2ui minus j, just 1, and then plus, it is going to be 0, right? It is going to be 0. So that is my cross product vector. What I need the length of this vector, which it is going to be equal 1 plus 4u squared. All right. Let me go back and then bring my integral here, 0 to the u. 5 I had here. Now the length of this vector is equal 1 plus 4u squared dv and then du. The rest is just your algebra skill, guys. The integral of dv is going to be just v, right? 0, 2, 5 times 1 plus 4u squared times v, 0u du, 0, 2, 5, 1 plus 4u squared, just u after using the boundary, and 0, look at u minus 0, which is u du. Did you see? It turns out to write the single variable integral. And then you should be remembering, right, what integration techniques you could use to solve this integral. I can use, the substitution when t is equal 1 plus 4u squared, dt is going to be equal 8u du, right? 8u du. Do I have the 8u somewhere here? No, I don't have. I have just the 5u, but look at that. I can use some algebra trick. I can multiply by 8. If I do this, 5 over 8, that integral would turn into, I'm not going to change the boundaries first. It's going to be equal square root t dt. If you take the integral, it is going to be equal t over 3 over 2, 3 over 2, 0, 2. And then I can put the u back, which is 1 plus 4u squared. Is there any question so far? I hope you are able to follow everything what I did here. As you see, right, I'm just following the formula I'm given by the surface integral. You see f times, this part is dc actually, right? I found the length of, this cross product. I just do the necessary operations. I don't know, okay, what this number is. Just say k, since you are going to need to use the calculator, but the number is not important actually, okay, for the question. So it might be any number, doesn't matter. But the next example, we are going to try to interpret the result actually. But for this problem, I just wanted to show you, okay, the computation part of the surface integral. That's how you calculate. If you are okay with this question, I have another example for you. Please let me know if you have any question before I start the next one. All right. First of all, you need to remember, okay, how the mass can be calculated, right? Mass normally can be calculated, right? The density times volume, right? You learn that way in physics, maybe at high school, at university. But if the if the surface is not given, right, like the plane or the simple ones, so the surface area should be calculated, especially for the flat and there's an assumption actually when you do this surface integral. This is how you calculate the mass problems, guys. Look at that. This is for the flat thin material. Okay, you can calculate the mass. This is your density function. Basically, the rest is just the surface area, but it is kind of, there's an assumption here when you calculate the mass, which you can calculate, right, the volume using the surface area here, since they are so flat thin material. That's why. Look at that. If you want to calculate the mass, I need to use this formula. Now let's go ahead and then solve a problem. Okay, so that how we can see how we can use this formula, guys. Flat sheet metal. A flat sheet metal has the shape of surface z is equal 1 plus x plus 2y that lies above rectangle 0x to the 4 and then 0y to the 2. Okay, this is the surface part. This is how your surface is given. One more statement about your density. If the density of the sheet given by rho xyz, x squared yz. So what is the mass of the sheet? All right. And then I know that I'm going to be using the formula I gave you to. Mass is calculated by the surface integrals, and I'm functioning the density function. I just need to go ahead and then use the density function in my surface integral. But the problem here, as I mentioned in my previous examples, you need to find a parameterization for your function, for your surface. What is your first surface? Surface is a plane basically here, right? And then you are being asked, the mass of the plane, since it's a flat sheet metal. Of course, it's going to be given basically by a plane function. As you see, there is no parameterization given here. How can I calculate the parameterization? How can I find the suitable parameterization? This is a remark, guys. If you are not given any parameterization for any given function, look at that. If you are given a function, but if you need a parameterization for this function, the simplest parameterization for any given function, since the parameterizations are not unique, you can find, more than one parameterization for any given function, but the unique parameterization could be this. Look at that. I can choose my U and V parameter. I can choose my U and V parameter this way. This is U, this is V. Okay, the letter names doesn't matter actually. You can go ahead and then use the UV. If I choose my UV as an X and Y respectively, X, Y, and then here what I'm going to have, as you know, this should be Z. Look at what the Z is going to be. Z is equal to f of x, y. Did you see that? So for my plane function, plane is given, from the example, for example, look at that. If Z is given 1 plus x plus 2y, the parameterization can be obtained using the same idea. X, y, and then the Z function is the f of x, y function, 1 plus x plus 2y. Did you see? That is how I can parameterize the given surface. Okay, if it is a parameterization, how am I going to find the mass? Mass can be calculated using the density function x, y, z, and then ds. And then as you know, right, that this integral on the left-hand side can be arranged this way over D. D is given, right, by the UV parameter, and then here X is given, since I assume, right, that my U is going to be X, my V is going to be Y. That's why I'm just going to put, right, the X and then Y boundaries here. The boundaries were given, if you remember, look at that. Boundaries were given this way. I'm going to go ahead and then put the boundaries for the X and Y. And then I need to go ahead and then use the parameterization in my density function. So density function was equal X squared Y, Z. X is X, Y is Y, X squared Y, but the Z is equal this one. This is why I'm going to go ahead and then use this way. Am I done? Not yet, since the S part should be calculated. The area, TU plus TS. Sorry about these sounds, guys. TU times TS, length of TU times here, of course, since I changed, right, the letters, I'm going to go ahead and then use the TX and then TY and then DS. And then when I use, right, the UMV, the variable can be the integral variable, right, now can be iterated over the dx and then dy. Now, right, the ds part is going to be dx and then dy, but you need to be careful about the order, which one you use first, right? Look at that. This is the x boundaries. That is why x should be at the outside, if you remember from the double integrals. Okay, so I still need, right, the tx and then ty part. What is tx and then what is ty? Okay, what is tx and then what is ty? How am I going to find them out? I'm going to find them out using, right, my parameterization. My parameterization, since my parameterization was xy, 1 plus x plus 2y, right? Let me write it down one more time. Let me not screw here. xy, which is equal xy, 1 plus x plus 2y. Now, by using, right, this parameterization, you are going to be finding out the derivative of t with respect to x, derivative of t with respect to y. T is equal actually r here, okay? It is just, we use just to denote the tangent, okay? That's why it is t here. The derivative of t with respect to x, derivative of x, which is 1, derivative of y with respect to x, which is 0, derivative of this part with respect to x, which is 1. Same thing for y, look at the 0, 1, and 0, 1, and 2, guys. What I will do, I will go ahead and then calculate this cross product and then the length of this cross product. But first I need to calculate the cross product. IJK 1, 0, 1, 0, 1, 2. Okay. If I do this for I, it is going to be negative I. And then negative j, 2 minus 1, which is going to be 2j. And then if you do for the k, plus k. So the length of, right, this vector is going to be, you need to use the length formula, 1 squared coming from here, negative 1 squared plus negative 2 squared, and then plus 1 squared, which is going to be equal to square root 6. All right. So I have everything I need, right? Look at it. I have this part, I have this part. So now let me go ahead. And then put everything back, 0, 4, 0, 2, x squared y, 1 plus x plus 2y times square root 6, right? This is the length of, right, this part, which goes here, and then dy dx. Did you see now? The rest is just, right, calculating the integral, I'm not going to actually do this integral. This integral is easy. Okay, after this part, just go ahead and then take the integral, partial integral, first integral over dy and then dx. Okay, it is going to be given 2,560 over 9 square root 3, something like that. Okay, so this is the mass. I think mass unit was the kilogram per meter, or the kilogram, just the kilogram. That is how I calculated, guys, mass. Let me go ahead and then repeat the steps, okay, one more time, what I did here. Look at that. This is the formula I'm gonna be using, but of course, this is the notational. And when I extend that formula, it is gonna be equal to, right, the rho xy times, right, the length of this cross product vector. What I do first, right, if I'm not given the parameterization, my first step, okay, is to find out what the parameterization is. And look at what I did here, right? For that purpose, I used the parameterization for general purpose, actually. This is, right, the parameterization for any given function you can do, right? You can just replace the u by x, replace the y by v, and then that's gonna be your parameter. And then just go ahead, right, to do the rest. Use your function, use your parameterization in your function. That's what I did here, right? In my function, in my density function, I use this parameterization. Otherwise, I can't solve, right, this surface integral. And then the rest is just, right, coming from the ds. Basically, it is coming from the surface area part, guys. All right, that's how we combine, right, the parameterization by surface area to get the surface integrals. Do we have any question? Okay. So that part was just actually the surface area problem, surface integral problem for the scalar vector field, scalar function, guys. But now we would like to go ahead and calculate vector field surface integrals. So surface integral for vector field. Surface integral for vector field. Obviously, it should be different than, right, the surface integral for scalar function. Look at that. That is how the surface integral is given by the scalar function. And then we did this, right, this way, f times tu times tv, right, the du dv. That is how, right, how I calculate. This is the calculation. This is just the conceptual, okay, formula. If you notice this, right, since this is a scalar function, that should be scalar so that I can multiply them and then I can take the integral of it. But if you put here the vector field, right, you can just say, why don't we just change, right, the function f with the vector field? If you just put here the vector field with big F, first of all, this is vector and then times scalar. Yes, of course, you can calculate, you can just multiply by a scalar, but the integral of, right, the vector is gonna be what? We need, right, especially when you are given such an integral, we need, right, a scalar at the end of, right, the day. The integral should give me, right, a scalar, but if you keep, right, this vector here, you can get the scalar. That's why you should be multiplying by something so that you can get the scalar. So that's the first thing you need to keep in mind. For this purpose, then I should be multiplying my vector field by something so that I can get the, right, the scalar or scalar function. If that was you, now remember how I found the surface area. I want to go through one more time, since we have something there we need to see, guys. Let's say this is my given surface. Okay, this is the surface. As you know, I map right under this parameterization to the surface. All right. If you remember the surface area problem we discussed, what we did, we used some tangent vectors. Now I want you to answer, please, since you are always silent. What is this cross product vector? I hope you still remember from the chapter, the first chapter. When you multiply these two vectors using the cross product, what type of vectors would you get? Any answer?
Unit vectors?
Unit vector. Anything else?
Orthogonal vectors?
Say it again.
Orthogonal vectors?
Orthogonal vectors. Do you agree, guys? Yes, John says the same thing. Yes, guys. If you still remember, that would give you a vector which is orthogonal to these two vectors. Look at that. This is the vector you will get, if you multiply these two vectors using a cross product. This is orthogonal vectors to this one. So now I am thinking this type of problem, like I said at the beginning, okay, you might have any vector field here, guys. Look at that. So you might have heat flow here, electricity flow. You might have force flow, speed flow, okay? There might be any type of vector field. If you remember, we did this similar thing, okay, for the line integrals. If you have the vector field here, to calculate this vector field, it might be like I said, the force field, any type of it. Since this surface exposed this vector field, I want to find out the effect of vector field on surface. Since the surface is exposed, this vector field, how am I going to calculate this exposition? I need to relate this vector field by this vector. If you remember that we did the same thing for the line integral, we use the projection of the vector field on the tangent vector when you deal with the line integrals. I will do the same thing. Look at that. If I want to calculate how much this vector field effect on the surface, I'm going to relate this vector by n. This is just the n at one point, one point. But the vector flows through, flows through across S. That is why I just need to multiply, to get the projection of F on N using the vector, using this dot product, guys. This is just for 1 point, This is just one point. But look at that, you have infinitely many points on S. That is why integral, will come into the play. If you have the infinitely many things, you can just go ahead and then add them up using the integral, That is why, there are a couple different reasons around I just discussed with you. I can define the surface integral this way. I hope you got the idea. Why I need to define the integral, surface integral, when you are given the vector field. Look at that. This is different, This definition, the surface integral definition, now is different than how you define the surface integral for the scalar field. You needed to take into account this vector across the surface. And then that's the reason, why we should consider including that vector. All right, now we are ready to give the definition. And I'm just going to show it to you how you can give the computational part of this integral. All right, definition. Let F be continuous vector field with a domain that contains oriented surface S with unit normal vector N. The surface integral of F over S is given by the formula I just showed to you. Yes. But what I like to do, I like to choose the N. Yes, N is the perpendicular to the right of those tangent vectors. I want to choose the N as a unit vector, right? Doesn't matter how you chose the perpendicular vector, but it is going to matter actually for the computational simplification. I will show it to you. Can you please tell me if N was this, right? How could you make this vector as a unit vector? Do you still remember that part? How could you make this vector as unit vector? Huh? Instead of taking N, okay, plain N, I want to make it right the unit vector. How could you do that? Answer? Do you have any answer, guys? Do you still remember? I can divide right the is by its length to make it right the unit vector. So that's now it's gonna be unit normal vector. Why I do this? Now I'm gonna show you. Since as you know, right, this surface integral now, since over the domain D, right, which this is the right the UV domain. Since you need to go ahead and then use the parametrization of your right the surface this way. If you use parametrization, the S part will be equal, as you know, from the right surface area discussion, which is gonna be this way, du dv. But the M part, look at the N part, is gonna be basically this, du times tv length. I hope you now see, okay, why I chose the N as unit vector, so I want to cancel these. If you cancel them out, you can calculate, right, the surface integral for vector field in this way, tu times tv. Now this is going to be look at the dot product, right? Since this is vector, and then also this is vector, you can multiply by a dot product, and then it's going to be du dv. Is that all right? Does everything make sense so far? I hope you got the idea how I, thank you, Nathan, how I got the, right, the vector field, thank you, Kira, surface integral for the vector field. And then this is the reason actually I'm using the N vector, okay, inside the surface integral. So basically surface integral, guys, will give you the answer to this question. How much fluid, okay, flows through across S? If you want to calculate this question, if you want to answer this question, this fluid could be anything as we discussed. This fluid could be heat. This fluid could be electricity. This fluid could be force field. All right. But you want to understand, you want to answer this question, you want to calculate actually how much fluid, how much, let's say, electricity, how much heat flows through right across the surface, maybe at any given moment, right? And then you want to calculate this, right? You want to calculate how much heat you need to produce, how much electricity you need to charge, right, that surface, maybe for other purpose on that surface, right? If you want to answer all these questions, of course, the surface integral will be necessary to calculate. Surface integral is also called the flux integral, guys. If you see around any term like the flux integral is basically surface integral or the vice versa. So now let me give you a short break, but after the break, actually, I'm going to show you a nice example about the surface integral. Then we are going to see the Stokes theorem, and then we are going to stop there. All right, guys. See you soon. All right, let's go ahead and then solve an example about the surface integrals for vector fields, guys. Example. So let V is given. This is the velocity field, guys. Is given this way: 2x, 2y, and z represent a velocity field The units for the velocity field, it is meters per second, guys. Meters per second. The velocity field for a fluid with constant density for any given point, with constant density, 80 kilogram per meter cube. Okay, this is the information about your function. There is another statement which gives us some other information about my surface. Let S be a sphere given by this equation, okay, which, since it is hemisphere, okay, I'm just gonna give some restriction on the z part. Okay, this is just a negative z part, such that S is oriented outward. Now, the question is, find the mass flow rate of the fluid across the surface. All right. So we are wondering, right, what is the flow rate per second of that fluid right across the surface? The fluid actually is defined by its speed velocity field, and then also it is density. So basically it is given by, we need to use this formula, guys, for the mass flow, the surface over surface. This is gonna be your basically function. You need to multiply your density by the velocity function. This is gonna be your F. And then you just need to use, okay, this formula to calculate the surface integral over the surface under given, right, this vector field, which is basically, it includes the speed and then density, right? All right, let's go ahead and then calculate, right, this mass flow And at the end of the day, actually, you are going to see the value of this surface integral for the calculating the fluid rate across any surface. So what I should do, I should be using my parameterization for this problem. So if I use my parameterization, first of all, I need to give a parameterization for the sphere. Do I know what the parameterization for the sphere, guys? I think we learned it, right? And then we used it on Tuesday class. You can give the parameterization this way. Theta and then phi for instead of u and v. Of course, you can go ahead and then use and then u and v, but this is the convention for the spherical coordinate system. Theta and phi I'm going to be using to parameterize my sphere. And then the radius of the sphere in this example is 9. That is why, sorry, it is 3, right? Since the sphere actually is equal to 9, that's why the radius is 3. So the parameterization can be given then 3 cosine theta times sine phi, 3 sine theta sine phi, and 3 cosine phi. All right, that's the first thing I should do. Second thing, I still need my boundaries for my parameterization terms. Theta is going to be between 0 and 2 pi. Normally, the phi interval should be given 0 to the pi, right? But here, since I am dealing with just the half of the sphere, that is why it needs to be divided by 2. All right. If you want to adjust the scan, the half of the sphere, you just need to divide the interval by 2 so that you can cover just half of it. Okay. The second thing, I need to go ahead and then find out what my t theta and then t phi so that I can calculate the cross product. T theta and then t phi. You need to go ahead and then take the derivative of the components with respect to theta and phi as well. -3 sine theta and then sine phi, 3 cosine theta sine phi, and then 0. T phi is going to be equal 3 cosine theta cosine phi, and then 3 sine theta and cosine phi, and then -3 sine phi. Right, guys? So what I should do, I should calculate the cross product this way, I, J, K. It's gonna be a little bit complicated. Just give me 1 second so I can see everything. -3 sine theta sine phi here, 3 cosine theta sine phi here, 0. 3 cosine theta, sorry, cosine t cosine phi, 3 sine theta cosine phi, and -3 sine phi. If you calculate the cross product, it is going to be equal 9 cosine theta times sine square phi, 9 sine theta sine square phi, 9 sine phi cosine phi. All right. Am I done? Not yet, since I need to go ahead and then use the parameterization in my function, right? This is my parameterization for my function. Function was equal, if you remember, 2x, 2yz. That is why it is going to be equal 2 times. So it is going to be 6 times cosine theta times sine phi, and 6 times sine theta sine phi, and 3 cosine phi. All right. Now I'm ready to combine everything here, right there. 0, 2 pi, 0, pi over 2, in my integral. So I'm just gonna go ahead and then use the parameterization here, as you know, which is this vector, 6 cosine theta sine phi, 6 sine theta sine phi, and 3 cosine phi. Times here, what I have, t theta times t phi, right? I need to bring this vector here, which is equal, 9 cosine theta sine squared phi, 9 sine theta sine squared phi, and 9 sine phi cosine phi d phi d theta. That is the integral you need to calculate, guys. Any problems so far? Are you able to follow everything what I have done so far? Is there any point you want me to repeat? I hope everything is fine on your side. As you see, this is the dot product. I need to take an agent. I need to just multiply these two vectors using the dot product, component by component, this component by this component. Look at this, 64 cosine square t times and sine cube phi plus, if you multiply this by this, you are going to get the same term actually. Sine square theta, except this term actually, sine cube phi, all right? Look at what I have. I have the like terms here, and then the rest is just going to be 1, since the two terms will give me 54 sine cube theta, sorry, phi. Okay. And plus, I'm just going to go ahead and multiply this by this, which is 27 sine phi cosine square phi. D phi d theta, 0 pi over 2, 0 2 pi. So the rest of this integral actually can be calculated using your integration technique skills, guys. What I will do, I can use some trigonometric identity here for the sine cube phi. This is going to be equal 1 minus cosine square phi times sine phi, right? Now look at that. When you multiply 54 sine phi here I have, and then minus 54 cosine square phi sine phi, which is basically, I have the similar terms here. You can just calculate, right, combine these terms. So that's what you are going to get, 54 sine phi minus 27 sine phi times cosine square phi. D phi, and then d theta, 0 pi over 2, 0 2 pi. This part integral is easy. It is equal negative 54 cosine phi. And you can just go ahead and then use, right, the substitution. If you say cosine phi is t, look at that, you have the dt here. You can use the power rule. It is going to be equal 27 cosine cube phi over 3. Okay, 0 pi over 2, still 0 2 pi, and then d theta. I just handled, right, the first part of the integral. The rest is just, okay, it's going to be easy. If you plug the pi over 2 and then 0, 0 2 pi, and then 45, and then this is d theta. But we forgot something actually since the beginning. What it was, look at that. You had the rho here. Rho was 80, right? It's given 80 as an 80. Look at the example, right? This is your density. I just need to go ahead and then multiply at each step 80. So 80 times 45 times theta, 0 to pi. When you calculate this one, it is going to be 72 hundredths pi. What is this? How can I interpret this result? That is the important part actually. I just look at that, went through the really complicated example, and then I found out that this is the number I need to be using. This is the mass flow rate, guys. Mass flow rate flowing across that surface. So mass flow rate is 72 hundredths pi kilogram second per meter square, guys. Do you see? I hope now you see the value of the surface integral. If you didn't have the surface integral, you couldn't know, you couldn't calculate this number actually for the surface and then for that density. And then trust me, a lot of actually companies use these type of models to calculate a lot of different substance, under these vector fields, these densities, for different purposes. And then in that case, they need to use some sort of surface integrals if they can parameterize the actually surface, since it is not actually easy to parameterize the surfaces. In any case, as you see, this is just a sphere. It is easy to find a parameterization for the sphere, but now we ask this question: if you have this really complicated shape, you would like, for example, like the car materials, You use some car materials in engine. In the engine, you have some different shapes actually you use. And then you want to understand how they are going to behave over time under that kind of the heat flow. For example, that might be the question. What would happen to those substances under that heat flow over time? So that is look at the surface integral. But the problem comes from how you are going to find a parameterization for those type of materials you would like to use in engine, for example. If that is the case, now Stokes theorem, guys, that's the actually end of the chapter 16. Stokes theorem says, don't worry, if you want to calculate, that was a whole lot of things. Yeah, you are right. So it was scary, to solve this type of surface integral, scary. But the Stokes theorem are going to be our hero today. Not always actually, but sometimes it says, don't worry if you have some complicated parameterization for your surfaces. I am here to help you, and then I can give you better way and easier way to calculate your surface integral. What is that way? That way is the line integral, guys. Stokes theorem actually gives us a connection between the line integrals we learned. Between line integrals and the surface integral, you're going to be able to use the line integral instead of the surface integrals, or the vice versa. If you want to solve the line integrals, you can use the surface integrals. But of course, there are some assumptions about the Stokes theorem, and then proving the Stokes theorem actually would be the hardest part of this class. That's why we are not going to get into that one. I'm just going to give you, the Stokes theorem, and then we are going to see an example of the Stokes theorem. Then we are going to stop there. Basically, you need to remember this about the Stokes theorem. If you don't remember anything about actually, maybe in a couple of months, since you are going to forget everything about this class. You just need to remember this one. Stokes theorem is basically a connection between the line integrals and the surface integrals. It simplifies the surface integrals using the line integrals. Also, second thing you might remember, Stokes theorem is the generalization of the fundamental theorem of calculus to the higher dimensions, guys. As you remember, I hope you still remember why do we need the green theorems? Do you still remember what purpose did we use the green theorems for? Green theorems was basically write a double integral. Instead of the line integral, you might be using the green integrals. So if you are stuck with the line integrals, you can go ahead and then use the green integrals, right? Of course, there was some conditions you need to satisfy always, but the green integrals was just a generalization of the fundamental theorem of calculus for line integrals. And then Stokes theorem is another generalization of the fundamental theorem of calculus. You might see that way. All right, let me give you the theorem after all these introductions. Let S be a piecewise, a lot of conditions here. I have a piecewise smooth oriented. This orientation actually, I'm not going to dive into that part. This orientation comes from the perpendicular vector we use in the surface integral, guys. The orientation comes from that vector direction, that perpendicular vector direction. Smooth oriented surface with a boundary that is simple, closed curve C with positive orientation. Okay, that is how we define my surface. If F is a vector field, with component functions that have continuous partial derivatives on an open region containing S. You see, we have a lot of different assumptions here. Then the integral of this vector field, but not the vector field itself. It is about the curl F. We have seen the curl F before right there. If you want to calculate the curl F over the surface, curl F was another vector field. If you remember, let me remind you how you calculated. That was the cross product of this gradient by the vector field, ijk. I hope you still remember delta U, delta X, delta Y, and then delta Z. And then these are the components of your vector field PQR functions, right? That is how you can calculate curl F. It is another vector field, actually. It is going to give you a vector field. So the vector field here I have, but it is a special vector field. If you want to calculate the surface integral of this vector field, which is calculated by a vector curl of any vector field, this vector field this surface integral can be calculated. Look at that by this line integral. You see the right-hand side of this formula. So basically, instead of using the surface itself, you can just go ahead and then use the curve, over that surface, over that surface. And you can just calculate the line integrals, over the boundary of the surface, which we can parameterize by C curve. That is what the Stokes theorem says. If you look at the right-hand side, guys, this line integral will be easier than the surface integral. Look at it. This is surface integral, and then this is line integral. Now I'm gonna show it to you an example. calculate integral, surface integral S curl F ds, where S is the surface oriented outward. I'm gonna show it to you what the surface is now by a picture, guys. Don't worry. And then F is given by this vector field. Look at the Z, 2xy, and then x plus y. Just give me 1 second so I can show it to you, the surface. All right. This is the surface, guys. And then look at the vector field around the surface. It might be like we talk about, okay, it might be heat flow, it might be electricity flow. This is kind of right a manifold in the engines, you might think, or some other materials you use around. I don't know where it is used. But the engineers, they want to calculate actually the flow, right? The fluid flows through right across the surface. Do you see the difficulty finding a parameterization for the surface, for this surface? It is almost impossible, right? Either you need to go ahead and then use a cylinder, maybe a lot of cylinders, and then do part by part, right? So it's kind of cylinders, and then it's still not easy. Or you can use the surface integral, Stokes theorem. Look at what it says. It says basically take the curve around the surface. This is surface, you see, but the curve around the surface is just circle, guys. Right, circle. Instead of using the parameterization of the surface, I can just use the curve parameterization. The curve is here, right? Basically circle. Do I know how to find the parameterization for the circle? Yes, we did a lot of times, right? The cosine t, sine t. Basically, curve is the two-dimension shape. That's why the z parameter could be anything here. It could be any number. So I'm just going to choose 1. This is my r of t. My f function was equal, right? My f function was equal z to xy and x plus y. As you know, to take the line integral f dr, I need to use, look at that, this parameterization. The parameterization of circle, of course, you need to give right the interval for your circle. Of course, it's going to be 0 to pi. When you have the boundary, now it is time to use the parameterization in your function r of t, and then it's going to be r prime t dt. That was the line integral. I hope you still remember. F of r of t, what is that? I'm just going to be using my parameterization in my function, which it is going to be equal 1, 2 times cosine t sine t, and then cosine t plus sine t. What is r prime t? R prime t is equal negative sine t, cosine t, and 0, and then dt. Did you see? It turned out to this integral. Now let me go ahead and then use the dot product. If you use the dot product here, multiply this by this, negative sine t. Multiply this by this, which is equal to cosine squared t sine t. Multiply this by this plus 0 dt. This integral is going to be easy to calculate, negative plus cosine t, and then say u, okay? U, if you say u squared du, that's going to be u cubed, which is 2/3 cosine cube t, and then 0 to pi. If you calculate this, guys, it's gonna be 0. That's gonna give you 0. Did you see? It was actually so complicated to calculate if you chose to go with the surface integral. But the Stokes theorem helped us. Don't worry, you can just use the curve around the surfaces instead of surface itself to calculate the same surface integral, guys. Of course, this could be anything, right? The interpretation actually depends on the application, depends on where you use. Either since the fluid mechanics and also the electromagnetism, if you are planning to take all those classes, you can see a lot of different examples, different application of the Stokes theorem. In multivariable calculus, we just deal with the math part, guys. I just try to teach you, the math part of all these things. Of course, if you're still wondering, the advanced part of this class, since as you see, we don't prove the Stokes theorem or any theorem. We proved a couple of theorem actually, but that wasn't a big deal. If you want to see the proof part, of course, you need to take some more advanced class for that part. But if you want to see the application part of how you can use for, which we haven't had so much chance, to see that part, you need to take some advanced physics class like the electromagnetism or the fluid mechanics in your later years. This is the point actually I'm gonna stop, guys, and then we have covered everything we needed to cover, and I have so if you have any question about your exam or about the final exam, since we are gonna have in 2 weeks, so please ask your questions. The review for the final, I extended the review until final day, guys. I hope you can complete all the questions, and it is going to help you a lot about the final. But since I assigned the final review actually in Thanksgiving week, since we haven't covered the Stokes theorem and the surface integral, there wasn't any question actually related to the surface integral. I can add a little bit more to there actually. You can go ahead and solve those and prepare well for the final exam. That is all I'd like to say. I hope you enjoyed the multivariable class, and thank you so much for joining me, guys. And thank you. I hope we see you again. Have a nice day.
Thank you,
guys.
Professor.
Thank you.
Thank you, Professor.
Thank you, Nathan.